Just reminder, this is the physical part of 204. With respect to the homework, you're going to get them immediately after class, and immediately after class I'm going to also post the answers. And you have until next Monday, same time, to resubmit if you want half the point you lost, assuming some of you have lost points. Okay? Some issues that were noted by Carrie, and I'll pass the word to her as well, is check magnitudes and units. Read the directions in questions. In graphs, make sure you have units on the graphs and that you're plotting what is asked for. And look also for significant digit. If something has an uncertainty that's relatively large, providing up that magnitude with 5 point after the decimal is not very useful. So actually, in the homework for today, you're going to have an exercise that has to do with significant units. Carrie, anything else?
Just in general, be sure to write your name on documents as Dr. Voss asked in his previous lecture, label when you send us your file, label it the appropriate way. Compile all your stuff into one document. Don't send us like Excel files and documents and put it all together in one thing.
And you can do it. I mean, it's a skill you need. So
yeah, there's no need to send us like all your data sheets.
You right-click on the graph and then to copy, and then you can save it in. I mean, you can paste it in a Word file. Yes. No.
You just send us
what we asked for
what's
is.
important.
So if there's a table with data we asked for, put that table in, but you don't need to.
And then just one big thing, especially because I had a lot of you for 201 figure calculus. Never do a figure without figure calculus. Okay?
And I know it's hard for you to imagine that, but we're building on one class upon the other. So we assume that the skill you had before, you'll carry with you. So it's not like, oh, I'm done with this class, I don't have to remember that stuff forever. We're trying to build up your skill sets in a serial fashion. So please, if you're not sure, just go back to that previous class. Again, the website has everything you want and more. You may want and more. Some important concepts from last week, just as a reminder. We talked about the no slip condition, the fact that fluid next to anything, be it a fish, be it the bottom, is at the same speed as that whatever at the interface between them. Okay, so if there's a solid object in the water that's falling through, the water right next to it has to go with that. This is what we call the no slip condition. We talked about the fact that we treat fluid as a continuum rather than treat it as 10 to the 22 different molecules per ml per centimeter cube, and follow the direction each one is going. We have found that it's convenient, and actually we can write equations that predict well the behavior of fluids by treating them as a continuum. We don't have to think about the individual molecules. And we talked about the fact that both viscosity and temperature are properties that have to do with the molecular nature of water. But this is the macro expression of the properties. For example, in the case of temperature, it's the kinetic energy of the molecule, how fast they move. And with respect to the viscosity, we said it's the diffusion of the momentum of these molecules. So if somewhere we have a rigid boundary, you remember from the lab, that moves slowly, that information about that motion penetrate into the fluid through this macro property we call viscosity. Okay, today we're going to talk a little bit about different quantities in the fluid, one of which is advective flux, and that's simply the fact that, and you'll have it also in your homework, is that when you want to know how much stuff moves in the fluid, you have to keep track of the cross-sectional area, the speed by which things go through. This will give you units of velocity times L squared, so it's L cubed per time. That will be the volume flux, area times velocity. And then if you multiply that by concentration, something per volume, you're going to get units of that something per time. That's the material flux. Okay, so when you talk about flux, we always talk about units of time. So in this case, if it's a concentration of a chemical. It might be mole per time, because we have a cross-section area times velocity times mole per meter cube or length cubed. If it's fish, I have, or mercury or whatever, let's say we have 100 fish and they overall don't swim fast, 100 fish per meter cube. And I have a cross-section area in a river that's 20 meter square, a velocity of 1 meter per second. That will give me a volume flux of 20 meter cube per second. And then if each of these meter cube had 100 fish, then all I have to do is just multiply by this 100 fish per meter cube to get the number of fish. In this case, it's going to be something like 2,000 that are passing per second in that cross-section area. So this is how we calculate fluxes. That's important because it helps you keep track of what's coming in, what's going out of places. And again, you'll have a homework assignment that's going to be based on this. We're going to get back to this, but before, we didn't talk yet about what determined the density of water. And I know that you know it because you've been in Dave Townsend's class, but just a reminder, when you deal with fresh water, so if I ask you a question about lakes in Maine, there is a temperature. Anybody remember? That's the one where the water has the maximum density. Anybody remember? Yes.
4.
It's around 4 degrees C. And at 4 degrees C, the water is maximum density. That means that when you cool a lake, the surface water get denser and denser, and they will convect down and down until you get to 4. When you get to 4 degrees, the lake is homogeneous. And then as you cool further, only the top of the lake is going to cool first, because that water is more buoyant than what's underneath. Does this make sense? The water at the surface, when you cool from 4 to 0, when you start forming ice, is going to be less dense than the water below. So that's for fresh water. For salt water, that's not the case. For oceanic water that are salty, the maximum density is below the freezing point. So the water, as you cool below 4 degrees, you're continuing to make denser and denser water. So these are two very different things that happen. Now, another thing that happens when ice is forming in the Arctic or Antarctica is the ice rejects the salts. As it's forming, it's an impurity. It rejects salts, it rejects or dissolve organic material, and that goes into the water below, making it even denser and even enhancing the convection below the ice. Just things that are important for you to remember. And also the fact that density in general for water decreases, so from 4 degrees, this is for pure water, decreases with temperature, but increases with pressure. So if I take the same water and put it under high pressure, it will compress, it will get denser. Not a lot, but it does. So water is, to a high degree, we're going to assume it's incompressible for everything we talk about. But just remember, it is slightly compressible. Slightly, the changes are order 4% per 100 meter here. This is 100 bar. No, this is 100 bar, not decibars. So this is 1,000 meter, I have a 4% increase in density. So it's not a lot for 1,000 meter. The average ocean depth is 3,000 meter. So just things to remind you. Oh, I know what we're missing here. Can you get me, Jim, please, the density tank?
Sure.
And a salt water and a fresh water? We'll do this later. I forgot to bring it. So in general, what you'd expect to see in the ocean is water that's less dense overlying water that's more dense. This makes sense to everybody. Okay? However, if you did a transect in the equatorial Pacific, you'd find that near Papua New Guinea, there's the warm pool. Very warm water extending down to about 40 meters. And as you go towards the Galapagos, towards South America, the water gets denser and denser, cooler and denser. And the question to you, okay, if that's the case, why isn't this water overriding the light water, here the red, the warm water, riding over the cool water on the other side? Anybody has an idea? Yes?
Water current?
Water currents?
Yes.
So you're saying there's currents going this direction. What's causing those currents? No. Winds. You said winds. So the prevailing winds in the equator are in this direction, and that's what's piling this light water at the western side of the equatorial Pacific. This is what we call a La Nina year. This is normal condition. When the wind stops blowing, this is what starts the El Nino. The El Nino is where these warm water actually flow to the other side. These warm water are relatively poor in nutrients. And in that process, there's fish killed in Galapagos, there's seals that are dying because they have no food. And all it is just this restratification of the ocean when the forcing ceases, the wind forcing ceases. This is what we call El Nino. Okay? So you cannot maintain a situation like this without continuous forcing that in the equator is provided by winds. Now, the rotation of the Earth, if this was in a different latitude, you would not be able to maintain it the same way because things will veer to the right. But in the equator, the effective Coriolis is 0, right at the equator. And this is why this is maintaining the same direction of the wind as opposed to 90 degrees to it, as it will happen in the northern hemisphere or to the left in the southern hemisphere. This is a cross-section across the Pacific Ocean, okay? From the north to south. And this is the first 1,000 meter. And what you observe is that, again, these are equal density line. And again, they're not a line across constant depth. If there were no forcing, everything should be a line straight. And I'll show you that in a second when Jim comes back with the demonstration. So when there's no forcing, things should be simply on a geopotential. Every density surface should be flat. So if they're not, that means to us there's forcing. So what do you think we see here? What are these two features that we see here, and what might cause isopycnal or density surfaces to be almost vertical in the northern and southern areas of the oceans? What do you think is happening? Let's start with these. What might cause density stratification to be almost, density surfaces to be almost vertical? They're not. I mean, this is, of course, exaggerated. What? Yes, if you cool from the top and sink dense water down, this is the type of features you'll cause. This is what you're going to cause because you're continuously cooling from the top and mixing stuff down. Okay, remember, on average, we're cooling all the time at the top and we're warming at the equator. So there's a temperature gradient going from the poles towards the equator. And then what might cause these feature? What do you think causes these feature, these two bulges? Have you learned? Yes?
The northern and southern gyres.
Exactly. These are the two gyres, two subtropical gyres, the wind-driven. And the only way we can maintain this the way it is through wind forcing, continual wind forcing, and it's in geostrophic balance. Again, these are concepts you don't have to remember. You'll see them again soon in 302. Most of you have not taken it. And you've heard about them in Dave's class. So thanks to Jim, we can go through this demonstration. For those of you who did not think that what I said is correct. So we have here two fluids. Let's try and put them somewhere here. I'll try and put it somewhere high. Move this, and I'll try not to splash. Thank you. Yeah, this is okay. Okay, so we have two fluids. One of them is more denser than the other. I don't know which is which. Is it wide enough? Can everybody see? What do you think is going to happen when I raise the partition? Less dense will go on top. And the other one? So what's going to happen to the interface between them that's currently this way?
It's going to get like swirling action.
It'll wedge, almost like a salt wedge.
It will wedge and then eventually come to rest this way. Do you want to come and raise the partition? If you don't mind. Thank you. Just so you don't think I'm doing magic on my own.
What do you want me to do?
Just raise the partition as fast as you can. Take it up. No. Now you're doing internal wave. Just take the bar in the middle and take it out.
Oh, okay.
Thank you.
What?
Up. Yeah, excellent. What do you see? Keep it out. You can keep it out. Thank you. So what's happening?
Yellow, less
The yellow is less dense. It's on the top. What did you see happening in the interface between the two fluids? Beside the mixing, did you see a wave sloshing from one side to the other? Have you heard about these waves? These are the biggest waves in the ocean. These are internal waves. They're much bigger than any surface wave you've ever seen. They can have amplitude of 50 meters. And they exist in all of the world's ocean. But that's what happened. That's where the energy goes for this and for mixing as we adjust the density. But finally, once forcing is over, we get a fluid that has two layers. Okay, so this is where the ocean would, if we stopped forcing on the ocean, all oceans would simply be stratified in this fashion. So the moment we see density surfaces that are inclined, forcing has to exist. Something is causing them to be. They will not be that way if there's no forcing. And you learn much more about it in 302. Okay, next. And now another concept, coming back to this flux I talked to you initially. This one has to do with conservation of mass of fluid in a system. So now let's assume we have a constriction. We have a river, and for whatever reason, it's easier to do it with pipes. Let's think about your veins. Your veins are constricting as they distributed to other parts of your body. And if we neglect for a moment compressibility of water, we said to a large degree the water is incompressible. You need thousands of meters of fluid above you to get a few percent of compression. Neglecting that for a second, whatever mass is coming through this area has to come here. Okay, and we said the volume flux is velocity times cross-sectional area. If that's the case and we change the cross-sectional area, what's the relationship between the velocity here and the velocity here? Which one is faster? V2 has to be faster. Okay, because we're requiring that the same amount of fluid goes through here than through here. If it did not, then you'll back up this fluid and you have to slow down. Okay? So thinking about it, think about at home, you have a hose. And you want the water to reach the other side of the garden from where you are. What do you do with your thumb? Simply put it in the front. As long as the force that is pushing is trying to push the same amount of fluid, this will accelerate. Okay, so as long as we're trying to maintain the same flux, then the fluid will accelerate. Now, just to convince you that water is not tremendously compressible, I have two balloons here. Okay? One of them has water in, the other one has air in. Okay, let's see if you can tell which one is which. So this is, you can buy this thing in the supermarket. It's a pump that evacuates the air. Okay, so I'm going to let air back in. So now it's low pressure. And let's look at these two and see if they change in size. Only one of them changed size. Which one was it? The one with air or the one with water? Air, because air is compressible. And if you reduce the pressure around it, it expands. Did it make sense? Super. Okay, so now we're starting to deal with fluid moving. So remember previous class, our fluids did not move. Now we're starting to think about what happened as they move. Same exact Newton's law of motion applied to water, just like they apply to everything else. So if change of momentum in time equal the force. If I apply a force on the wall, the force apply exactly, and the wall does not collapse, apply exactly the same force back on me. Okay? So that's the second. And so if you want to generalize it to a fluid, it's everything around you. And now we can also talk about momentum flux. If momentum is mass times velocity, momentum flux will be momentum times velocity times the cross-sectional area. If we, so rho v squared times a. Everything we talk about flux has to be whatever it is, time velocity, time cross-sectional area. Where I here note the small v is for velocity, the large v, if I use it, is for volume. Mass flux, as we said before, will simply be the mass times velocity, time cross-sectional area. So there's an additional v there for momentum. And similarly, we can do for energy and everything else. So now we'll move also to talk about pressure and stresses. We talked about them before. We talked about the fact that pressure is a force in the normal direction per unit area. So again, I'll need somebody here to volunteer. Who's going to be? Rebecca. So I have here a bed of nails and I have a balloon. And Rebecca is not going to put huge amount of pressure, force on it, but she's going to put enough that you'll see it squishing on top of the bed of nail.
That's not right. I'm worried about popping it.
Well, it's not popping. Okay, now let's try it with a single nail. Okay, so now the force is distributed over many, many heads of nails, and therefore the pressure on each nail is less. Okay? And the pressure on the balloon in every given point is less. Now apply the same force on this one nail. Sorry.
I knew it was coming
Sorry.
anyway.
It had to come. Thank you, Rebecca. So, again, the fakir in India is not the superhuman. We're distributing the same force on a much larger area, and therefore the pressure is less. And what matters for your skin, what matters for the balloon in terms of buckling, is the amount of pressure that's applied. Think about a sharp and a dull knife. A dull knife, all it does, if you apply the same pressure on a bread or on your hand, is not going to cut you because it's distributed over a larger area. What you do when you're sharpening is that the same force is going on a much smaller area, and therefore it can cut. It can cut meat, it can cut bread. Okay? So pressure is what matters, not the force, because it's distributed on it. So it's force per unit area. That's the most important thing about a pressure. I talked about sharp versus blunt. Within a fluid, pressure is not a vector. It's a scalar, but it goes in the direction that's perpendicular to the sides. And then we come to the concept of hydrostatic pressure. Hydrostatic pressure is the pressure that you feel when you dive. It's a pressure simply due to the fact that there's a mass of fluid above you. So it's the mass of everything that's above you divided by area. Again, force per unit area. So it's the density, mass is, remember, mass is volume times density. And if it's force per unit area, it's volume times density divided by area. And then I'm missing something. F is equal ma. In this case, it's weight, so it's g, my acceleration due to gravity. And then if I take the cross-section area, the volume is simply the depth of the fluid times density times the gravitational constant. So this is pressure. Pressure is rho times g times h. Density times the acceleration of gravity times the depth of the fluid. So every 10 meter of water, every 30 feet, has the same amount of pressure as 1 atmosphere. Our atmosphere. Our atmosphere, on average, the pressure we feel due to the atmosphere is equal to the pressure due to 10 meter of fluid. So if I dive to 10 meter, how much did the pressure increase? To 30 feet, how much did the pressure increase from what it was at the surface? If an atmosphere is 10 meter, and I go down to 10 meter, how much did the pressure increase? By 1 atmosphere, or it doubled. So I'm doubling the pressure just by diving 10 meter. Now, if you don't believe me that there is an atmospheric pressure, this is just a piece of plastic. Try to get it off the table. You can't. And the reason she can't, or the reason it's very hard, is because the atmosphere is weighing on it. Okay? This is why. And if any one of you is welcome to try. Now, why could I do it when I moved it around is because now the pressure here and the pressure here are the same on both sides of it, which is not the case here. When I'm trying to remove it, there's some air in here, and this air, as I pull it up, I expand it, and the pressure decrease underneath it as I'm trying to get it off. Okay. Well, I will get to ideal gas in a second, because that's where the fun begins. Oh, there's a problem. Okay. These are problems I have. So now I'm going to move to there. We have a big dam here. Here there's a dam, and here there's a lot of water. This is H2O. This depth is H. So I have the atmospheric pressure on this side. I have the atmospheric pressure on this side. And let's ask ourselves, what's the force acting on this dam? Simply because there's water on one side and there's none on the other side. Just like, think about this tank we had. If I had the partition and only filled one side of it. Okay, so I have atmospheric pressure here. I have atmospheric pressure here. That's the same everywhere. So this is a dam, and then we might release it and stuff is going to go down. But you might say, well, if there's no force on it, I can build it any size I want. There's no issue. But there is an issue. I mean, dams do break, and it makes a lot. And the reason they break is that there is a net force in this direction. What causes this net force? Let's think. Here, in the fluid, pressure increases as function of depth. We just said pressure in a fluid is density times rho times h. Okay? So the pressure just at the half point here is going to be, that's in the water, in the fluid, is going to be rho times g times h over 2. At the bottom, just to the fluid, it's going to be rho gh, and will increase in general as function of depth. If I have this depth and this is pressure, in the fluid it's going to go from 0, this is pressure of the fluid, from 0 to rho gh. Okay? And then on top of it I have the atmospheric pressure. So this point is actually, if I want to know the total pressure, I have to add the atmospheric pressure. And in the ocean, as you know, we often increase down our axis. So what's the average pressure on this dam? What do you think? If it's going linearly, at the bottom it's rho gh, here it's rho gh over 2. What's the average of this curve, of this triangle? Come on, you can do it. What's the average pressure? Here it's 0, here it's rho gh. So as we go towards each other, what do we converge on? Exactly. The average pressure in the fluid is rho gh over 2. If you wanted to know how to calculate it, you simply do integral of the pressure as function of depth divided by integral of depth. This will be the P average. And you're going to get, this is rho GH, or rho GZ. And so you're going to get Z squared over 2 divided by Z. And so the Z squared is going to go, and you're going to end up with rho GZ over 2. Okay, so we can do this. So now we know how to build it such that so if we know this, what's the force that's acting on that dam? Now there's atmospheric pressure on both sides, so that cancel. These are two forces that cancel. What's the force acting on the dam? If I know the pressure, how do I do the force? Pressure times what is force? Come on. Pressure times what? No. No. That's force is mass times acceleration. That's correct. But the relationship between pressure and force. What did we say? What did we just say about the balloon? I had force, and then to get the pressure, what did I need to take care of? Area, exactly. So the total force acting on the dam is the area of the dam times the pressure. So the bigger my dam, the more force is acting on it to try and break it. That could break it, not to try, but it could. And this force is directed outwards. So it's no surprise that when they collapse outside and not inside. Okay, so the average force equals the area times the average pressure. No magic. Okay? So now we're going to do the diver case. So now you're a diver, and you like to dive, and you're diving from the surface with a mask, and the mask is about 15 centimeters by 10 centimeters. This is you. And it's strapped behind your head, and you're diving from the surface to 10 meters. And the question I have to you is how much pressure, if you don't put air into the mask with your nose, would you feel on your face? So we're at the surface, the pressure in is equal to the pressure out, no problem. It's atmospheric pressure. When you're down here, what's the pressure outside? It's going to be, the pressure is density times, again, and density is about 1,000 kilogram per meter cube, or 1 gram per centimeter cube, whichever units you want to use. Just be consistent, times h. So this is, we say, 10 meters. This we say 1,000 kilogram per meter cubed. And this we're going to say 10 meter per second square, just because it's convenient. Okay? And now I want to know the force. So this is the pressure. And we said this pressure is 10 times 10, 100 times 1,000, 100,000. Excellent. 100,000. We have kilograms there. We have per second square per meter. Now I want to know the force on your face. Okay? The force on your face, the extra force, because in addition to it, I also have the atmospheric pressure, but that's exactly countered by the atmospheric pressure inside. So the force will be this times the size of your mask. That's what's going on your face. So it's going to be 10 centimeters, so this is going to be 0.1 times 0.15 times 10,000. So I can now, this is going to be 1 if I take 1 out of here. So 1,000 times 0.15, that's 1.5, 15, 150 Newton. This is equivalent to a person of what mass sitting on your mask? If you assume again, so if you say this is equal to mg, and G is about 10, the mass is going to be 15 kilogram. Is this correct? 15 kilogram. They seem too low for me. Something is missing here. This was 100,000, sorry. So this is 1,500. And this is 150 kilogram. 150 kilogram is somebody more than 300 pound sitting on the mask. Okay, so you do not want to go down with a mask where you cannot equalize the pressure by blowing with your nose air back into it to 30 feet. And any one of you who tried to, just with small goggles even, to dive down to only 10 feet comes back with rings around their eyes because of the extra pressure simply from the fluid. Okay? Anybody dives here? Oh, good. So now, hopefully, this will ring some bells. And we have another demo. Up. So how can I keep a balloon from collapsing? I'm not putting any pressure on it.
Oh no, it's just the stopper on there.
There is a stopper at the end. What happens if I take the stopper out? Okay, so Jim came up with an ingenious way you could make it yourself. So here is a Coke bottle. Same story exactly. You don't need a fancy $100 piece of Pyrex to do it. You can do it yourself. So what's happening here? What keeps that balloon from collapsing? Yes?
There's no way for air to get behind the balloon to equalize the pressure inside of the bottle, because the balloon will build up the only way for air to get in.
So yeah, air cannot come into this side.
So the pressure can be equalized for the balloon.
The pressure cannot be equalized. But we need to talk about it. So we're going to go to a lesson in chemistry you learned for sure. What's the ideal gas law? Again, something you probably checked out and thought you'll never have to see again. Anybody remember? Ideal gas law, yes. Exactly. So we have PV equal NERT. Okay, these two are constant, we don't have to deal with. What are the P, the V, and the T? Pressure, volume, and temperature. Okay, let's assume there's no change in temperature here. So we don't have to deal with these at all. So pressure and volume in a gas go in opposite direction. This has to stay constant if temperature is not changing. So what happens when I fill it up with air? I increase the volume. The pressure, when I let it go, will be the atmospheric pressure. So at this stage, there's a volume here. The pressure here is atmospheric. What happened to the gas here? The gas here, and we have the balloon trying to collapse it. The balloon is trying to collapse. When the balloon is trying to collapse, it's trying to expand the air here. If it expands the air here, which it does to some degree, the volume goes up, the pressure goes down. So here we have low pressure now in the air, and that's lower than the atmospheric pressure in the opening. And that force from high to low pressure is what keeps the balloon open. So the balance of force is between the pressure change. There's a high here compared to low here because it's tried to expand that air by with the elasticity of the balloon, and then the elasticity going the opposite direction. So pressure, the force due to the pressure is equal to the elastic force of the balloon at this stage, and that's why nothing happens. According to Newton, if nothing happens, all forces are equal and opposite. And then if I let go, now the air can expand easily. There's less pressure here air is going to flow from high to low pressure and get into this bottle. So look how much physics there is in a balloon in a Coke bottle. Build one. Play with it. It's fun. What else do I have? Oh, the other stuff is not for now. Let's move on. Okay, so now we'll talk a little bit about pumps. Pumps are mechanism by which we increase pressure in one place compared to another. By what we call raising the head is having fluid that's higher, because if the fluid is higher here than here, then flow will go from the higher pressure to the lower pressure. We have several kinds of pumps. There's one that's positive displacement. If we decrease the volume, just like we do here, or bicycle pump, we can raise the pressure. Again, using this law, if we decrease the volume, we raise the pressure. That's a positive displacement pump. And then we have those that are based on fluid dynamics, are based on moving fluid. And what happens is when you accelerate a fluid, when you move fluid fast, the pressure at that place drops. These tend to be better in producing high pressure, and those are better in moving stuff fast, moving water through. Here is an example. What kind do you think this kind of pump is? It's fluid dynamic. We're moving fluid around. Exactly. So here are two movies that I want you to see, two short movies. One is about a sponge. And you have a diver coming, releasing fluorescein-dyed water next to a sponge. And you'll be able to see how. So what do you think, how do you think, a sponge is a colony of unicellular organism. What do you think they have that might cause this fluid to cross to the other side? Yes? Cilia, exactly. So that's one that is accelerating the flow, is moving fluid around. This is one thing. The other thing that we'll learn about is when flow, if there is a flow going above a chimney, there's lower pressure produced here because the fluid has to accelerate, and that sucks fluid through. Now another organism that uses a pumped fluid to move are cephalopods. Let's see if we can watch this one. So this is a Nautilus, and it's basically producing a jet. It gets water coming from the side and it jets it backwards, and by that it advances. So it has to pump water in and then eject it in the back in a coherent way. And that's what allows it to move in water. Pretty cool organism. We'll see it in a second being higher up in the water column, not just walking on the bottom. Here. Pretty impressive. All this mass is moving simply by a jetting fluid through its orifice. Okay. Next. So fluid moves from region of high to region of low pressure. Okay, so that's the direction of the force, because force is equal mass time acceleration. You can think of acceleration as being dv dt, which is what it is. Changes in velocity equal F over m. F over m is F over a over a length scale over rho. This is mass. So this is pressure. So change acceleration equal, it turns out, 1 over density. It comes straight from here. Changes in pressure as function of length. So this is a fluid dynamic equation that describes to you how acceleration in a fluid happens. So it goes in opposite, it goes from high pressure to low pressure. That's why there's the minus sign here. One of the applications of these concepts is the hydraulic press. And you'll play with it in the lab today. because the pressure is transmitted throughout the fluid, by increasing pressure on a small area, which allows me to use less force, but over a longer distance, because again, force is pressure times area. If I have less of an area, I can apply less force to get the same pressure as will cause a car to be jacked up. But it has to be over a longer distance. So I have to go further down here, then I'll go just a little bit up here. And that is the general concept behind hydraulics. And that's because pressure is transmitted throughout this fluid. And taking into account the fact that force is pressures time area. You'll play with it in the lab today. We talked a little bit about the ideal gas law, the Pvnurt, but just so you can see an applet of changes of temperature there's a little simulation here. There are plenty of them on the web. They're really, really cool. Let's see if we can see something. Run. Yes. So in these simulation, you can simply change. I'm trying to stop it for a second. Yeah. By changing, it simulates what molecules do, and by changing certain boundary condition, for example, that if you put a heater on the bottom, you can see what it does to the momentum of the molecule. Again, energy has to do with the average momentum of molecules, the kinetic energy. So if I put a heater on the bottom and let it go, you're going to see it accelerate, and you can see there'll be a change here in the distribution of the energy. You see it's going to higher and higher. As we're heating the one in the bottom, we're giving them more and more energy. So that's, again, going back from statistical mechanics to what actually happens in, back to here. Pressure has to do with momentum transfer. In a container, it has to do with the molecules bumping with the sides. This is what maintains it if you want to look at it from the perspective of an ideal gas. And again, we talked about viscosity being momentum transfer between molecules. So all these things are properties, pressure included, that come from the molecular nature of the water or the air. But we see them in the macro. We just feel the pressure acting on us as if it was a continuum and in our scale. We did the change of volume and pressure. That's the one we just did. And we did this. So this is done. Okay, finally, diving and pressure. We talked about the fact that as you go down, pressure increases, which means that if you have a problem with your nose or with your sinuses, and you dive and you cannot equalize pressure, you can get these cavities to get damage and blood to flow into them. So very important, you don't dive when you have the colds, because air needs to be able to balance. We have about 6 cavities in our head that need to be able to adjust. Where you have fluids or solids in your body, no problem. It's only in places where you have air and they're in your face and in your ears. This is why we have to do the adjustments. Why can't we do a snorkel all the way very deep? Why can't I simply have a snorkel going on the surface and me going as deep as I want? What do you think? Yes?
The pressure on the snorkel.
It's not the pressure on the snorkel, it's the pressure on your chest. So as you go down, and the atmospheric pressure is what you have inside your, but you're right, it could be also on the snorkel. You're absolutely right. But it's also on the person. You're here, and the pressure here is much larger than the pressure at the surface. And so you need actively with your muscles to keep that cavity against the pressure of the water from collapsing, given that there's much less pressure for the air coming in than there is pressure from the fluid collapsing. So snorkels are effective, up to a foot, maybe a few feet, but not more than that. Afterwards, you just can't get the air in. You can't fill up with air from there. And what you need is compressed air that comes from your scuba bottle that can fight the pressure from the water itself, the fluid itself. Another thing that happens when you dive is that gas increase their solubility with pressure. That's not a problem when you go down, but when you come up, it's a problem because if you come up too fast, you can form bubbles in your blood, and those bubbles can block your vessels. So this is one of the reasons why you have to come slowly to the surface and take stops along the way if you stay too long. So what do you think marine mammals might do when they dive very, very deep to avoid getting their lungs to collapse? I mean, some of them let them collapse, but some do not. What might act against this collapse so that things don't, get stick to each other? Yeah.
Strong ribs.
Strong ribs again, but it's very hard to work against pressure when you go that deep. Yeah.
Hemoglobin?
You can have fluids going into your lungs to maintain it. If you have a fluid is highly incompressible, it's not going to collapse. So if you let fluids get into your lungs, you can keep them from collapsing. And then that fluid will come out slowly as you surface. That's one strategy, one mechanism. And we're right on time. Any questions before we? So Carrie has your homework if you want them right now. I'm going to post the homework shortly. I'll see you in the lab. Those who we did not take pictures of, we'll take pictures of. That's it. See you.